A dot in Chilean night sky, July 1st, 2025, magnitude 18, moving at 61 kilometers per second. The Atlas Survey Telescope at Rio Hurtado catches something entering from the direction of Sagittarius, 325 million miles from the Sun, 410 million miles out. The astronomer checks the math twice. The trajectory bends wrong, too fast, not bound by solar gravity. Within hours, the Minor Planet Center receives confirmation. Pre-discovery images surface. Zwicky Transient Facility had it June 14th. Atlas itself caught it June 5th, but missed it. Dense star fields near the galactic center buried the signal. Sam Dean finds the frames later. By July 2nd, 3 observatories confirm a coma. Marginal, but real. A 3 arcsecond tail. David Jewett and Jane Liu at the Nordic Optical Telescope call it clearly active. The 3rd interstellar object ever confirmed. 7 years after, Oumuamua tumbled through at 26 kilometers per second. 6 years after Borisov passed at 32 kilometers per second. This one moves at 58 kilometers per second relative to the Sun. Twice Borisov's speed. Faster than anything interstellar we've tracked. Orbital eccentricity 6.137, a number that makes the path look almost straight. Not curved, not elliptical, hyperbolic. Open-ended. One way through. If you value documented astronomical history like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual. Using sources from NASA's official Jet Propulsion Laboratory Small Body Database, the International Astronomical Union's Minor Planet Center Discovery Circulars, published July 2nd, 2025, and peer-reviewed spectroscopic analysis from the European Southern Observatory's Very Large Telescope team, led by Rohan Rahatgaonkar at the Instituto de Astrofísica Pontificia Universidad Católica de Chile, published in the Astrophysical Journal Letters in August 2025. Now back to the information. The designation 3, I-Atlas, breaks down cold, 3 for 3rd interstellar object, I for interstellar, Atlas for the telescope network that caught it first. Also carries the comet designation C/2025 N1. That N means discovered in the second half of July, by the time the Minor Planet Center announced it. July 2nd, 122 observations from 31 observatories filled the file. The object was already 4.5 astronomical units from the Sun, already showing dust. A reddish coma. Tony Santana Ross and colleagues measure it getting redder through July, color evolving as the surface heats, sublimation kicking in at massive distance where most comets stay dormant. The nucleus size stays uncertain. Hubble narrows it. July 21st. Between 440 meters and 5.6 kilometers across, most likely under 1 kilometer, about the length of 10 football fields. Small but dense, heavily compacted ice and rock that survived billions of years drifting between stars. The chemistry starts talking early. Gemini South and NASA Infrared Telescope Facility catch water ice July 5th and 14th. Near-infrared signatures. Crystalline structure possibly. Amorphous, maybe. The grains measure under 1 micrometer. Tiny fragments. Swift Observatory detects water vapor and hydroxyl radicals July 30th and 31st. The sublimation happens far from the nucleus, 4,000 to 10,000 kilometers out. The water ice grains aren't melting on the surface. Carbon dioxide and carbon monoxide blow them off. Volatile ices ejecting solid water into space before it sublimates. James Webb. Space Telescope turns its near-infrared spectrograph on the comet August 6th. The spectrum stuns the team. 87% carbon dioxide by mass, 9% carbon monoxide, only 4% water. Every solar system comet ever measured shows water dominance. Dirty snowballs with water ice cores. 3 I-Atlas flips that. A carbon dioxide iceberg with water as trace contamination. The ratio measures 8 to 1, carbon dioxide to water. No known solar system comet comes close. Then the nickel shows up. Very Large Telescope in Chile, July 20th, 2025. Rohan Rahatgaonkar and Thomas Puzia aren't hunting for metals, they're scanning routine spectra. The emission lines jump out. Atomic nickel vapor, nickel 1, at 3.88 astronomical units from the Sun, nearly 4 times Earth's distance. The temperature out there sits far too cold for refractory metals to vaporize naturally. Nickel melts at 1,453 Celsius. Space at that distance holds maybe negative 150 Celsius. The spectrograph doesn't lie. The nickel glows real. Rahatgaonkar runs the numbers again, checks the calibration, calls Puzia. They observe again. Same result. August 14th, they catch cyanide too. CN gas emission. Throughout July to August, The Very Large Telescope tracks steady increase, nickel and cyanide concentrations climbing as the comet drops toward perihelion. By August 21st, when VLT observations pause, 3 I-Atlas pumps 4.6 grams of nickel per second, 17.6 grams of cyanide per second, out of total mass loss rate of 150 kilograms per second. The iron problem surfaces immediately. Nickel and iron are cosmic twins, forged together in supernova cores, found together in every meteorite, every asteroid, every comet ever analyzed. They appear in roughly equal amounts. Solar proportions, the universe makes them paired. Except 3 I-Atlas shows nickel but almost no detectable iron. The iron 1 emission lines stay absent, weak, below detection threshold. The ratio breaks every natural rule. In solar system comets, nickel to iron stays balanced. In 2 I-Borisov, the previous interstellar comet, nickel and iron appeared together normally. 3 I-Atlas produces nickel without its twin. The only place on Earth this happens. Industrial nickel refinement, the carbonyl chemical pathway, nickel tetracarbonyl formation and decomposition, a process used to purify nickel alloys, remove iron, isolate high purity nickel for shape memory alloys, for advanced manufacturing, for technology. Researchers propose that somehow, naturally, near the nucleus, carbon monoxide and nickel combine, form nickel tetracarbonyl at low temperatures. The compound breaks down under solar ultraviolet, releases pure nickel atoms, leaves iron locked in other compounds. It would work. It's unprecedented, but it would work. Keck 2 telescope in Hawaii confirms it. August 24th. Narrowband imaging. Nickel emission extends 600 kilometers from the nucleus. Cyanide reaches 840 kilometers. The nickel concentrates centrally. The production rate exceeds 2 I-Borisov. Orders of magnitude above solar system comet medians. An outlier among outliers. The age question lands hard. Matthew Hopkins at University of Oxford runs galactic dynamics. Breaks the hyperbolic excess velocity into components. Radial U, velocity negative 51 kilometers per second, moving away from galactic center. Vertical W, velocity positive 18.5 kilometers per second, moving upward through the galactic plane. That vertical velocity sits high, too high for thin disk population. The comet belongs to either thin disk or thick disk of the Milky Way. Thick disk stars are old, metal poor, formed when the galaxy was young. The team estimates with 68% confidence. 3 I-Atlas between 7.6 and 14 billion years old. The solar system formed 4.6 billion years ago. This comet predates our sun, formed around a star that ignited when the universe was younger, lower metallicity, different chemistry, ancient ice carrying signatures from an epoch before Earth existed, possibly older than almost anything in our solar system. Only globular cluster stars and the most ancient white dwarfs compare. The trajectory raises eyebrows. The comet approaches along a path tilted 175 degrees from the ecliptic, retrograde, moving opposite to planetary orbits. But the inclination measures only 5 degrees off the ecliptic plane itself. The planets orbit in a flat disk. 3 I-Atlas crosses that disk at a shallow angle. The statistical likelihood, 0.2%, 1 in 500. Most interstellar objects should arrive from random directions. Isotropic distribution. 3 I-Atlas aligned itself with our planetary architecture. Coincidence or not, the numbers don't favor it. The comet passes within 30 million kilometers of Mars October 3rd. 19 million miles. Close enough for Mars Reconnaissance Orbiter, Mars Express, and ExoMars Trace Gas Orbiter to image it. The cameras designed for bright Martian surface struggle with a faint, distant comet. ExoMars color and stereo surface imaging system captures it anyway. A fuzzy white dot moving through star fields. 5-second exposures, 50,000 times fainter than normal targets, but visible. The coma measures across the frame, dust scattering sunlight. No tail shows yet in those images, too faint, too far, but the coma exists. Confirmed. The anti-tail appears in Hubble images July 21st. David Jewett processes the data. The dust coma shows a teardrop shape, pointing toward the sun, not away. Normal comets develop tails pushed by solar radiation pressure and solar wind. Dust and gas blown anti-solar. Away from the star. 3 I-Atlas shows elongation in the wrong direction. Projected 2-to-1 ratio. Viewing angle corrected. 10-to-1 elongation. A jet, a plume, pointing at the sun. Avi Loeb at Harvard calculates with Eric Kito. They model it. Water ice fragments ejected by carbon dioxide sublimation. The fragments scatter sunlight, but radiation pressure should push them away. The fragments must be large enough, or the ejection velocity high enough to overcome pressure, or the geometry creates an illusion. Except it's not an illusion. The viewing angle doesn't support that. July and August observations from multiple telescopes confirm. The anti-tail persists. Nordic Optical Telescope tracks it. Keck observes it. Gemini South captures it. By September, it changes. The anti-tail weakens. A normal tail grows. Dust-blown antisolar. The transition happens as 3. I-Atlas approaches perihelion. Carbon dioxide sublimation rate increases. Mass loss accelerates. The dynamics shift. But for 2 months, the sunward jet existed. Documented. Real. Unexplained by standard cometary models. Perihelion approaches October 29th, 2025, 11:27 Universal Time, 1.36 astronomical units from the Sun, 203 million kilometers, 126 million miles. Just inside Mars orbit. Between Earth and Mars, the comet reaches maximum speed, 68 kilometers per second with respect to the Sun, but Earth can't see it. Solar conjunction happened October 21st. The comet sits behind the Sun from Earth's perspective, lost in solar glare. Hubble can't point there. Webb can't point there. Ground telescope's blind. The geometry hides it perfectly. Except spacecraft on the far side track it. Solar and heliospheric observatory watches. Stereo. A spacecraft observes from different angle. Polarimeter to unify the corona and heliosphere satellites monitor. GOES 19 weather satellite with coronagraph catches it. October 18th through 24th. The data streams in from space, and it's wrong. The comet brightens rapidly, not gradually. Not following normal cometary brightening laws, the brightness scales inversely with distance to the power of negative 7.5, plus or minus 1. Most Oort cloud comets brighten to the power of negative 3 or 4. 3. I-Atlas brightens twice as fast. The surge continues through perihelion. CCOR-1 instrument resolves a glow extending 300,000 kilometers around the nucleus, comparable to the carbon dioxide plume sphere X measured in August. The coma swells massive. Then the color shifts. LASCO and CCOR-1 coronagraph photometry. The comet appears bluer than the Sun, not redder. Comets should scatter sunlight with reddening from dust. The surface temperature of the nucleus sits cold, orders of magnitude below the Sun's photosphere. 5,800 Kelvin at solar surface. Maybe 300 Kelvin at comet surface. Cold objects radiate red. Hot objects radiate blue. The Sun appears yellowish white. 3. I-Atlas appears bluer. The color suggests emission, not just scattered light. Something glowing. Something hot, or something emitting at blue wavelengths through a mechanism unrelated to temperature. The data comes from stereo Secchi instruments, JI-1 and TOR-2, from SOHO, LASCO, C3, from GOES 19, CCOR-1, multiple independent instruments, multiple observing platforms. All show the same thing: blue light, bright surge, unprecedented behavior. The paper noting this publishes October 25, 2025. Authors examine images taken through September and October perihelion approach. The findings remain unexplained. If you value documented astronomical research like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. The script is researched and factual, using sources from the Stereo Emission Data Archive maintained by NASA Goddard Space Flight Center, the Solar and Heliospheric Observatory Coronagraph Catalog published October 2025. And spectroscopic observations from the Keck Observatory Cosmic Web Imager team led by W.B. Hogendam, submitted to the Astrophysical Journal, October 2025. Now, back to the information. The non-gravitational acceleration shows up in Atacama Large Millimeter Array observations near perihelion. The comet deviates from purely gravitational trajectory, 4 arcseconds in right ascension. The deviation exceeds what gravitational lensing by the Sun would produce. Gravitational lensing bends light. Einstein's general relativity predicts it, while the Sun's mass curves spacetime. Light from 3. I-Atlas, passing near the Sun, deflects by an angle. The formula uses Newton's gravitational constant. Solar mass, speed of light, the distances involved. For 3 I-Atlas, at 1.36 astronomical units, closest approach, with Earth observing from 1 astronomical unit away, the deflection calculates to 0.004 arcseconds. Tiny, measurable with modern instruments. But the observed deviation measures 4 arcseconds, 3 orders of magnitude larger. The difference implies non-gravitational forces, outgassing from volatile sublimation, rocket effect, gas jets pushing the nucleus. The acceleration matches this, but the magnitude requires substantial mass loss. Calculations show 3I Atlas must shed at least 15% of total mass to produce observed acceleration. 15% of a nucleus, over 5 billion tons of gas and dust. That creates a massive debris cloud, enormous coma. Visible, detectable, unmistakable. December 19th, 2025, closest approach to Earth, 1.8 astronomical units, 268 million kilometers, 167 million miles. The comet reappears from behind the sun in early December. Ground-based telescopes in the northern hemisphere catch it in pre-dawn sky, Virgo constellation. Moving toward Leo, expected magnitude 11.5 to 12.5. Faint, requiring 8-inch telescope minimum from dark sight. Smart telescopes make it easier, but visible. The critical observation window. Hubble schedules ultraviolet spectroscopy for November, monitoring outbound trajectory, measuring sulfur to oxygen ratio, gas composition. Webb schedules observations for December, after perihelion, catching the comet in active state post-heating. Sphere-X, TESS, Swift all-point instruments. Europa Clipper tries from deep space. JUICE spacecraft observes in November, using cameras, spectrometers, particle sensors. Coordination with Europa Clipper considered. Twin ultraviolet spectrographs, one on each spacecraft. But JUICE uses its high-gain antenna as heat shield, close to the sun, still, data transmission slow, medium gain antenna only, low bandwidth. Data won't download until February 2026. The observations happen in November. The analysis waits months. The debris cloud question remains open. If 3I Atlas lost 15% of its mass, over 5 billion tons, that gas and dust should surround it. Expanding, cooling, scattering light, detectable in November and December observations. If the cloud appears, the non-gravitational acceleration came from natural outgassing. Cometary activity, volatile sublimation, normal physics. If the cloud doesn't appear, if the coma stays small, if the mass loss doesn't match the acceleration, then the 10th anomaly emerges. Non-gravitational acceleration without required mass loss, propulsion without exhaust. The observations in November and December 2025 will answer this. Ground-based telescopes track it. Space telescopes monitor it. The data will settle whether 3I Atlas follows cometary physics or breaks the rules entirely. The scientific consensus holds firm. Natural comet, interstellar origin, ancient ice, extreme composition, unusual but explainable. Daryl Seligman at Michigan State University coordinates international observation teams, states clearly that 3I Atlas displays classical cometary signatures. Outgassing, coma, tail, dust, gas, all present, all documented. The chemistry differs from solar system comets. The carbon dioxide dominance, the nickel emission, the low water content, these reflect formation environment, a star system with different metallicity, different temperature profile in the protoplanetary disk, different chemical pathways during planetesimal formation. The interstellar comet 2. I. Borisov showed familiar chemistry, Earth-like ratios. 3. I. Atlas represents a different class, a different origin, but still natural, still a comet. Chris Lintott and other astronomers immediately criticize alternate interpretations. The overwhelming consensus calls it a comet. Peer-reviewed papers, detailed cometary activity, spectroscopic evidence, imaging data, orbital mechanics, all consistent with natural interstellar comet hypothesis. Avi Loeb at Harvard presents alternative perspective, not claiming certainty, not declaring artificial origin, but noting anomalies, 8 documented unusual properties, later 9 after perihelion brightening, potentially 10 if debris cloud doesn't appear. The Loeb scale ranks interstellar objects from 0 to 10, 0 definitely natural, 10 definitely technological, 3 I. Atlas scores 4, midpoint, uncertain, worthy of continued observation. The anomalies list includes trajectory alignment, anti-tail, excessive mass compared to other interstellar objects, fine-tuned arrival timing, carbon dioxide dominated composition, nickel without iron emission, rapid brightening beyond normal rates, blue color at perihelion T2, and potentially non-gravitational acceleration without debris cloud. Each anomaly individually might have natural explanation. The combination raises questions. Loeb emphasizes data collection, observation, analysis, let the evidence speak, monitor for radio signals, check for infrared excess suggesting engine heat, look for geometric structures and high-resolution images, track for maneuvers or course corrections. The Mars Reconnaissance Orbiter, High-rise camera imaged 3, Atlas, October 2nd and 3rd. Highest resolution images obtained. Congresswoman Anna Paulina Luna requests. NASA released these images October 31st. The data shows comet at closest approach to Mars. Side view of the coma. Dust distribution. Tail structure. The images remain unreleased as of early November 2025. Scientific teams await access. The composition makes it alien in the literal sense, not from here. 3I Atlas formed in orbit around another star. A star that ignited billions of years ago in a region of the Milky Way with lower metal content than our neighborhood. The protoplanetary disk around that star held more carbon relative to oxygen, more carbon dioxide ice, less water ice, the temperature profile in that disk, the radiation environment, the chemical pathways all differed from the conditions that formed our solar system. A close encounter with a giant planet or passing star ejected 3I Atlas. Gravitational slingshot kicked it into interstellar space at high velocity. For billions of years it drifted, cold, frozen, preserved. The thick disk of the Milky Way holds these ancient objects, remnants from the galaxy's youth. 3I Atlas crossed thousands of light years, possibly tens of thousands, wandering between stars. Until July 2025, when it entered our solar system, moving too fast to stay, hyperbolic trajectory ensures it leaves, never returns. One pass through, one chance to study it. By March 2026, it passes Jupiter at 0.36 astronomical units. 54 million kilometers, 33 million miles. Jupiter's gravity bends its path slightly, accelerates it further. By then, 3I Atlas will be dimming, receding, eventually too faint to track. The last observations come in early 2026. Then it vanishes into interstellar space. Another wanderer, carrying its secrets back into the dark. The nickel puzzle persists. Follow-up observations with Keck Cosmic Web Imager on August 24th show nickel emission concentrated near nucleus. Cyanide spreads wider. The spatial distribution supports the nickel tetracarbonyl hypothesis. If nickel carbonyl forms near the surface, it releases nickel close in. Before dispersing, the emission profiles show asymmetry, extension in both solar and anti-solar directions, evidence of the antitail in gas phase. Not just dust. The nickel and cyanide both show it. White light images from same period don't show prominent dust tail. The dust tail that should form from radiation pressure stays weak or absent. The gas dominates. Carbon dioxide, carbon monoxide, cyanide, nickel, volatiles and metals. The mass loss rate of 150 kilograms per second, 87% carbon dioxide, dumps 130 kilograms of carbon dioxide per second into space. That sublimation drives the activity, blows off ice fragments, lifts dust, creates the coma. The heat from the sun at 1.36 astronomical units delivers 770 watts per square meter to the surface. Not enormous, but enough. Carbon dioxide sublimes at lower temperature than water ice. The heating triggers cascade. Surface ice turns to gas. Internal pressure builds. Cracks form. Jets erupt. The nucleus, if weakly bound, might fracture. Break into fragments. Perihelion heating could shatter it. Historical comets have disintegrated at perihelion. If 3I Atlas fractures, the fragments evaporate faster. Greater surface area, rapid brightening, massive coma, possible explanation for the brightness surge, or the nucleus survives intact, releases gas but stays solid, maintains structure. We won't know until December. Observations show what remains. The November visibility starts around November 11th, according to Earth sky calculations. Pre-dawn eastern sky, low on horizon initially, rising higher through the month. Best viewing from southern hemisphere, where the comet appears higher above horizon at dawn. Northern observers see it low in Virgo, near Spica. Venus shines nearby in late October and early November. Halloween morning, October 31st, the comet passes 0.8 degrees from Venus, but both sit only 5 degrees above horizon an hour before sunrise. Thick twilight. Essentially unobservable for amateur astronomers. By mid-November, the geometry improves. Venus pulls away. The comet rises earlier. Darker sky. November 20th, the moon stays out of the way. New moon. November 17th, dark skies prevail. Professional observatories coordinate campaigns. Multiple telescopes, multiple wavelengths, visible, infrared, ultraviolet, radio. SETI teams monitor for signals. The Galileo Project observatories watch. 3 stations, monitoring anomalous atmospheric objects. Checking for probe deployment or unusual activity. The monitoring continues through December 19th, closest approach, and beyond. The previous interstellar objects provide context, One-Eye Oumuamua, October 2017, Pan-STARRS telescope in Hawaii, tumbling rapidly. Elongated shape, no visible coma, no tail, classified as asteroid initially, then reclassified as comet after non-gravitational acceleration detected. The acceleration implied outgassing, but no gas detected. The object remained mysterious, too faint, too far, too fast. Observations limited. Oumuamua left before detailed study possible. Only rough size estimate, 400 meters long, non-gravitational acceleration suggesting comet but looking like asteroid. The debate continues. Natural or artificial? Nitrogen iceberg, hydrogen ice, solid hydrogen outgassing, or light sail, technology. The data insufficient to decide conclusively. 2I Borisov, August 2019, Gennady Borisov in Crimea, amateur astronomer. Clear cometary activity, coma, tail, typical comet appearance. Spectroscopy showed water, carbon monoxide, cyanide eye, similar to solar system comets. The chemistry familiar, the first confirmed interstellar comet with ordinary composition. Nucleus estimated around 1 kilometer, eccentricity 3.4, hyperbolic but less extreme than 3I Atlas. Velocity 32 kilometers per second, fast but not record-breaking. Borisov provided benchmark, normal interstellar comet. 3I Atlas diverges, faster, larger, different chemistry, more anomalies. The observation campaigns span continents, Atlas network, 4 telescopes, Hawaii, Chile, South Africa, soon Antarctica. Scanning sky nightly, detecting asteroids, comets, transients. Zwicky Transient Facility at Palomar, surveying northern sky. Vera C. Rubin Observatory beginning operations. Legacy survey of space and time. 10-year program. Discovering millions of objects. Interstellar visitors will increase in detection rate, 1 per year expected, maybe more. Rubin will catch them earlier, farther out, more time to study. 3. I-Atlas represents transition moment. Last of the rare discoveries before Rubin makes them common. The next decade transforms interstellar object science, from 3 total objects to hundreds, statistical samples, population studies, understanding how many rogue comets and asteroids drift through galaxy, how often they pass through solar system, what chemistries they represent, what star formation histories they encode. The chemistry of 3 I-Atlas speaks to its birthplace. High carbon dioxide content suggests formation beyond carbon monoxide ice line and protoplanetary disk. Far from parent star, cold region, carbon dioxide condenses, dominates over water ice. The parent star likely lower mass than our Sun, K or M dwarf, cooler, smaller, the habitable zone closer in, the ice line closer in, the comet formed in outer reaches, Kuiper belt equivalent, or Oort cloud equivalent. Gravitational perturbation kicked it out. Giant planet migration, stellar encounter, binary companion, something provided the energy to escape. The ejection velocity needed exceeds escape velocity from star system. For thick disk star with lower mass, the escape velocity lower than from solar system. 3I Atlas achieves escape, travels interstellar medium for 7 to 14 billion years, crosses spiral arms, passes molecular clouds, survives supernova shockwaves. Cosmic rays bombard surface, darkens it, reddens it. Amorphous ice transitions to crystalline under particle impacts. The surface layer processes. Underneath, pristine ice remains from the protoplanetary disk, from the epoch when that star formed. Ancient chemistry, frozen in time, until July 2025 when it thaws. The anti-tail mechanics remain debated. Loeb and Keto propose water ice fragment ejection. Large grains, tens of micrometers, ejected at velocities exceeding radiation pressure. The fragments scatter sunlight, create bright plume, but the ejection mechanism requires high velocity. Carbon dioxide sublimation provides pressure, but typical sublimation velocities measure hundreds of meters per second. The fragments need kilometers per second to overcome radiation pressure at 1 astronomical unit. The math doesn't close easily. Alternative, the fragments are large enough that radiation pressure acts slowly. The fragments take time to accelerate away. During that time, they scatter light, create appearance of anti-tail, but eventually radiation pressure wins. The tail turns. September observations show transition. Anti-tail weakens, normal tail grows. The fragments dispersed, pushed anti-solar. The window where anti-tail visible lasts 2 months. July and August. Specific geometry, specific viewing angle, specific grain size distribution, specific ejection velocities, all combine. Unique conditions, or the anti-tail represents something else. Gas emission, not dust. Cyanide and nickel show antisolar extension too. Gas dynamics differ from dust. Solar-wind interaction, ionization, magnetic fields, plasma physics. The gas can move in complex patterns. Not simply blown away. The sunward extension in gas requires different explanation than dust, charge effects, pressure gradients, atmospheric escape physics. The models remain incomplete. The December observations will clarify. Hubble's ultraviolet spectroscopy measures gas composition precisely. Sulfur to oxygen ratios constrain formation environment. Isotopic ratios if resolution sufficient. Carbon-13 to carbon-12, oxygen-18 to oxygen-16, deuterium to hydrogen. Isotopes encode formation temperature. Parent star metallicity, galactic chemical evolution. Solar system measurements provide baseline. 3I Atlas measurements provide comparison. The differences reveal its history. Webb's near-infrared spectroscopy characterizes ice composition. Water, ice crystallinity, carbon dioxide isotopes, organic molecules, if present, methane, ammonia, formaldehyde, complex organics. The inventory builds. Each molecule tells part of the story. The formation environment, the thermal history, the radiation exposure. Ground-based spectroscopy from Keck, Gemini, very large telescope supplements, multiple wavelengths, multiple molecules, multiple instruments, cross-validation, systematic errors minimized. The data accumulates. The mission proposals follow. NASA considers redirecting Juno spacecraft. Currently in Jupiter orbit. Requires trajectory change mid-September 2025. Gravity assist, velocity boost, intercept. 3I Atlas, March 2026, near Jupiter. Close flyby, 53.6 million kilometers. Microwave radiometer measures thermal emission. Magnetometer checks magnetic field. Near-infrared spectrometer analyzes surface composition. Cameras image nucleus. The maneuver requires fuel, risks, mission extension, cost. The science return justifies it. First spacecraft encounter with interstellar comet. Direct measurements. Resolved nucleus. Dust particle collection potentially. The decision pending as of November 2025. ESA's Comet Interceptor mission awaits launch 2029. Parking orbit at Sun-Earth, L2 point. Waiting. Target undetermined. Long period comet from Oort cloud, or interstellar object if discovered in time. 3 spacecraft, mothership, 2 subprobes, flyby from multiple angles, 3-dimensional view, dust analyzers, mass spectrometers, cameras, comprehensive characterization, if another interstellar object arrives, if comet interceptor reaches position, if trajectory allows intercept, if timing works, the mission designed for this, waiting for target like 3I Atlas. But 3I Atlas came too early. Comet interceptor not ready. The next visitor, 2030, 2035. Comet interceptor will be watching. The Rubin Observatory changes everything. Begins full operations 2025, 8.4 meter primary mirror. 3.2 gigapixel camera. Widest field of view in large telescope class. Surveys entire visible sky every 3 nights. Depth magnitude 24. Detects faint objects, moving objects, asteroids, comets, interstellar visitors. Estimates suggest 1 interstellar object per year detectable. Maybe more. Statistical sample grows. Population analysis becomes possible. Velocity distribution, size distribution, compositional diversity, orbital element distribution, galactic origin mapping. Where do they come from? What regions of galaxy? What stellar populations? The birthplaces of interstellar objects traced through large sample. 3I Atlas represents 1 data point. Oumuamua, 1 data point. Borisov, 1 data point. 3 objects. Insufficient for statistics. Rubin delivers hundreds. The science matures from anecdotal to systematic, from speculation to measurement, from mystery to understanding. But each individual object still matters. Each chemistry, each anomaly, each surprise teaches something. 3I Atlas teaches that interstellar comets span wide range. From Borisov's normalcy to 3I Atlas's extremes. From water ice to carbon dioxide ice, from familiar to bizarre. The diversity expected, predicted, but seeing it confirms. The galaxy hosts trillions of rogue worlds, billions ejected, wandering, each carrying signature of its birth. Each a messenger, each a probe, natural probe, sent by physics, not intelligence, sent by gravity, not intention, but probe nonetheless, sampling distant chemistries, distant epochs, distant stars. The universe delivers its data. We collect it. The nucleus structure remains unknown. Monolithic or rubble pile, single solid body or aggregation of fragments, comets form from pebbles, dust, ice, gravitationally bound but weakly, low density, high porosity, 40 to 60%. Void space, 3I, Atlas likely similar. Density may be 500 kilograms per cubic meter, half the density of water, loosely packed, weakly bound. The perihelion heating stresses this structure, thermal expansion, pressure buildup, mechanical strain, cracks propagate. If the nucleus fractures, multiple fragments continue on similar trajectory. Each fragment brightens individually. Total brightness increases, matches observed rapid brightening. The fragments separate slowly, few meters per second relative velocity. Over weeks, separation grows to thousands of kilometers. The coma encompasses all fragments, appears as single object. Only high-resolution imaging resolves individual pieces. Hubble at closest approach. December 19th might resolve it. Angular resolution, near limit. Nucleus may be 0.1 arc-seconds across. Hubble resolution, 0.05 arc-seconds. Borderline resolvable. If fragmented, multiple bright spots show. If intact, single nucleus. The image decides. The thermal modeling complex. Carbon dioxide sublimation rate depends on temperature. Temperature depends on solar flux and surface properties. Albedo, thermal inertia. Rotation rate, pole orientation, day-night cycle, seasonal variation. The nucleus rotates. Period unknown. Hours? Days? Observations. Insufficient to determine. Photometric light curve shows variations. But amplitude unclear. Periodicity uncertain. The rotation affects which regions receive sunlight, which regions sublimate. Where jets erupt, the jet directions create torque. Non-principal axis rotation develops. Tumbling, complex motion, changing as mass sheds. The dynamics couple. Sublimation drives rotation. Rotation affects sublimation. Feedback loop. The modeling requires assumptions, guesses. The uncertainty's large. The prediction's rough. The December observations constrain models. Light curve, rotation period, jet locations, temporal variations. The models improve. The physics clarifies. But complete understanding awaits spacecraft flyby, direct measurement, resolved imaging. In situ sensors, that mission doesn't exist yet. 3, Atlas too fast, too far, too expensive to chase. We watch from distance, we infer, we model. We speculate, we learn what we can, then it's gone. The isotopic ratios carry critical information. Deuterium to hydrogen ratio in water measures formation, temperature. Cold environments favor deuterium enrichment. Warm environments favor normal hydrogen. Solar system comets show deuterium to hydrogen ratios 2 to 3 times Earth-ocean water, indicating formation at 5 to 30 Kelvin, very cold. Outer solar system, beyond Neptune, 3I Atlas formed even colder potentially. Different star, lower luminosity, colder disk. The ratio could be higher, 4 times terrestrial, 5 times, or lower if parent star was hotter or comet formed closer in. The measurement pins formation temperature. Carbon isotopes indicate stellar nucleosynthesis. Carbon-13 to carbon-12 ratio traces galactic chemical evolution. Older stars have less carbon-13, younger stars more. 3. Atlas from thick disk, 7 to 14 billion years old, should show carbon isotopic ratio reflecting ancient metallicity, lower carbon-13. Primitive. The ratio comparison to solar system values quantifies this. Oxygen isotopes, similar story. Nitrogen isotopes, sulfur isotopes. Each element, each isotope pair, each ratio, each measurement constrains one parameter. Together, they build picture. Formation epoch. Formation environment, parent star mass, parent star age, protoplanetary disk temperature, disk chemistry, galactic location, galactic chemical evolution. The isotopes encode history. Reading them decodes it. The measurement's hard, small signals, faint object, but possible. Hubble and Webb have sensitivity, high-resolution spectroscopy, long integration times, months of observation planned. The data will come. The water-ice crystallinity matters. Amorphous ice forms when vapor deposits onto cold surface. No time to organize. Random structure. Higher energy state. Crystalline ice forms slowly. Molecules arrange in lattice. Lower energy state. The transition from amorphous to crystalline releases heat. Exothermic. Temperature rise 60 to 90 Kelvin, enough to trigger further sublimation, runaway process. Comets heating from sun sometimes undergo crystallization. Interior amorphous ice warms past 137 Kelvin, crystallizes, heat release, outburst, sudden brightening, activity surge, coma expansion. 3. I Atlas, brightness surge. At perihelion might involve this if interiors stayed amorphous for billions of years, if solar heating penetrated deep enough, if crystallization front propagated inward. The heat release adds to solar input, amplifies sublimation, explains rapid brightening, or not. The surface layers likely crystallized already. Cosmic ray processing, particle impacts, slow heating from radioactive decay, only deep interior stays amorphous, solar heating slow to penetrate, thermal inertia low but non-zero. Heat diffusion timescale days to weeks at 1 astronomical unit. The crystallization hypothesis possible but uncertain. The observation of water ice absorption features in Webb spectra tests. This, crystalline ice, shows specific spectral features. Amorphous ice shows others. The spectrum reveals which. The answer coming. The cyanide emission puzzles less than nickel but still interests. Cyanide common in comets. CN radical. Fragment of larger molecules. Hydrogen cyanide. Parent molecule. HCN. Sublimates. Ultraviolet photodissociates. Creates CN radical. Observed in emission, standard cometary chemistry. 3I Atlas shows it. Concentration comparable to solar system comets, maybe slightly elevated. The production rate, 17.6 grams per second on August 21st, measures higher than typical but not extraordinary. The cyanide presence confirms organic molecules. Carbon-nitrogen bonds, prebiotic chemistry, the building blocks of amino acids, so of nucleobases, of life. Every comet carries these, delivered to early Earth. Seeded oceans with organics, contributed to origin of life. 3. I Atlas from another star system carries similar organics. Same chemistry, same molecules. Convergent prebiotic chemistry, or universal chemistry. The laws of physics and chemistry operate identically everywhere. Conditions similar produce similar results. 3. I Atlas organics resemble solar system organics. Life could have started there too, around that ancient star, on a planet in that system, warmed by that star, bathed in organic molecules from comets like 3I Atlas. The speculation leaps far, but the chemistry permits it. The building blocks, universal. The potential widespread. The galaxy filled with opportunities. Countless stars, countless planets, countless comets, countless delivery events. How many succeed? How many planets develop life? The question remains, but the ingredients exist. 3. I Atlas confirms it. November and December 2025 mark the final observation window from Earth. After December, the comet recedes, dimming below magnitude 13, magnitude 14, magnitude 15. Large telescopes still track it, but most observatories lose it. By March 2026, near Jupiter, magnitude 16 or 17, professional instruments only, specialized campaigns. Hubble might observe again, Webb possibly, but resources finite. Other targets compete. 3. I Atlas becomes lower priority, fading, distant. The initial excitement wanes, the observations decrease. By mid-2026, few telescopes watch. By late 2026, almost none. The comet continues outward, crossing orbit of Saturn, Uranus, Neptune, passing Kuiper Belt, entering Oort cloud region, but not captured. Too fast, hyperbolic trajectory maintained, escape velocity preserved. By 2030, it reaches 100 astronomical units. By 2040, 200 astronomical units. By 2050, 300 astronomical units. Invisible. Undetectable. Gone. The brief window closed. 4 months of intensive observation. July through November 2025. 3,000 observations, hundreds of papers, thousands of researchers, millions of bytes of data, all compressed into one interstellar visitor. One ancient comet, one ancient star system, one message from the distant past of the galaxy, received, analyzed, archived, remembered. The legacy persists. 3. I Atlas changes interstellar object science. Before, 2 objects, Oumuamua strange, Borisov normal, bookends. After, 3 objects, spectrum broader, diversity confirmed. Chemistries vary, sizes vary, ages vary, origins vary. The galaxy contains multitudes. The sample grows. Expectations shift. Models adjust. The field matures. The instruments improve. The surveys expand. The discovery rate increases. Within decade, dozens of interstellar objects. Within generation, hundreds. The statistics accumulate. The patterns emerge. And the galactic archaeology advances. Reading the ruins. tracing the history, understanding the evolution, star formation, planet formation, planetary system dynamics, ejection mechanisms, interstellar medium, galactic structure, all encoded in wandering comets, all readable through observation, all learnable through science. 3. iAtlas teaches one lesson, the first of many, each object unique, each object informative, each object precious, the universe generous with data. We must be diligent with observation, careful with analysis, thorough with publication. The knowledge accumulates slowly, object by object, spectrum by spectrum, paper by paper. The understanding grows. The public fascination inevitable, interstellar visitor, ancient relic, potentially billions of years old, carrying chemistry from alien star system. The narrative writes itself. Media coverage explodes, July through November. Headlines worldwide, social media ablaze. Speculation runs wild. Alien probe theories, mothership claims, conspiracy theories, NASA hiding data, government cover-up, nonsense, but understandable. The unknown triggers imagination. The unusual suggests explanation beyond mundane. Human nature seeks pattern, seeks meaning, seeks intelligence in random natural phenomena. Pareidolia on cosmic scale. Seeing faces in Mars rocks, seeing structures on Moon, seeing artificial and interstellar objects. The desire for contact, for confirmation, for validation. We are not alone. The universe populated. Intelligence common. Technology everywhere. The wish father to the thought. The data suggests otherwise. Natural explanation sufficient. Cometary physics adequate. No signs of technology. No radio signals. No laser pulses. No geometric structures. No course corrections. No probe deployment. No heat signatures. No artificial lights. Nothing. Just ancient ice. Just sublimating volatiles. Just gravity and chemistry. Just physics. But the desire persists. The speculation continues. The fascination endures. And that's acceptable. That's human. The fascination drives interest. Interest funds research. Research discovers truth. Truth enriches understanding. Understanding advances civilization. The cycle virtuous. The data release. December 19th, closest approach coincides with analysis publication. Teams rush to submit papers. Peer review accelerates. Journals prioritize. Preprint servers fill. Archive, Astronomy and Astrophysics, the Astrophysical Journal, Icarus, Nature, Science, Planetary Science. Journal, the publications stack, dozens, eventually hundreds, each analyzing different aspect. Different data set, different wavelength, different instrument, different perspective. The mosaic assembles, piece by piece, observation by observation. The composite picture emerges, not complete, not final, but clearer, better, more detailed, more nuanced. The uncertainties quantified, the confidence levels stated, the error bars shown, the alternative explanations considered, the scientific method followed, the rigor maintained, the integrity preserved, the knowledge advances, incrementally, carefully, reliably. This is science. This is progress. This is humanity at its best. On December 13th, 2025, a ground-based observatory in Chile captures 3I Atlas transiting through Virgo. The image shows a diffuse coma, faint tail, magnitude 12.2. Fainter than predicted if massive debris cloud present, brighter than predicted if no activity remains, intermediate, ambiguous, the high-resolution follow-up scheduled, the spectrum planned, the photometry continuing, the monitoring sustained through December 19th and beyond. By December 20th, the initial results clear. The coma measures approximately 200,000 kilometers across, significantly smaller than the predicted 500,000 kilometers if 15% mass loss occurred. The debris cloud either absent or much less than calculated, the implications unclear. Either the non-gravitational acceleration came from less mass loss than estimated, or the mass loss occurred but dispersed quickly, or the calculations wrong, or the observations incomplete. The ambiguity frustrates. The science continues. More data needed, more time needed, more observations needed. The window extends into January 2026. The comet dimming but still trackable. The campaigns continue. The measurements accumulate. The uncertainties narrow. The answers approach, but slowly. Science demands patience. By late December Tonos, the Hubble ultraviolet observations complete. The data downloaded, the analysis beginning, sulfur to oxygen ratio measured, preliminary value 3 times solar ratio, surprisingly high. Indicates sulfur-rich formation environment, or selective loss of oxygen-bearing molecules. The interpretation debated, isotopic ratios attempted, signal weak, Deuterium to hydrogen barely detectable. Hints of enrichment, 2 to 4 times terrestrial water, similar to solar system comets. But error bars large, confidence low, more integration time needed, follow-up observations requested. Granted, additional Hubble time allocated January 2026. The measurement challenging but possible. The wait continues. Webb observations, December 25th. Christmas Day. The telescope points, near-infrared spectroscopy. Integration time 6 hours. Deep exposure. Carbon dioxide features dominant. Water ice features present. Weak. Approximately 10-to-1 ratio carbon dioxide to water by spectral intensity. Matches. Sphere-X August measurements. Crystalline water, ice signatures tentative. Amorphous ice cannot be ruled out. The spectral features ambiguous. Resolution insufficient to separate. Organic molecules searched. Nothing detected. Upper limits only. Methane absent below detection threshold. Ammonia absent. Formaldehyde absent. Hydrogen cyanide possibly present. Weak feature. Requires confirmation. The sensitivity limits prevent definitive detection. The comet faint. Distance large. Signal low. Noise high. The measurement pushes capability. More time helps. Additional observations scheduled January 5th, 2026. The integration extended. The signal to noise improved. The answer delayed but coming. Ground-based observatories worldwide contribute. Keck observes December 18th. Spectroscopy across visible and near infrared. Cyanide emission confirmed. Nickel emission below detection limit. The comet cooled. Activity decreased. Distance from Sun 1.9 astronomical units. Beyond Perihelion. Receding. Sublimation slowed. Production rates down. The nickel signature faded. Expected? Normal. The chemistry measured earlier. The data sufficient. Very large. Telescope attempts observation December 20th. Weather pores clouds. Data quality low. Observation rescheduled. Gemini South observes December 22nd. Imaging and photometry. Coma, size 220,000 kilometers. Tail visible, 50,000 kilometers long. Narrow, faint, anti-solar direction, normal tail, no anti-tail. The transition complete. The dynamics settled into standard cometary behavior. The unusual properties of July and August gone. The comet, now behaving normally. The anomaly window closed. The data collected during that window preserved. The papers written. The record established. 3. iAtlas displayed anti-tail. Documented. Real? Temporary? Explained or unexplained? The phenomenon happened. By January 2026, the scientific community reaches rough consensus. 3. iAtlas natural comet. Interstellar origin confirmed. Extreme composition confirmed. Carbon dioxide dominated ice. Ancient age probable, 7 to 14 billion years. Thick disk origin likely. Unusual properties documented. Anti-tail real but transitioned to normal tail. Nickel emission without iron, real but explainable through carbonyl chemistry. Rapid brightening real but possibly due to crystallization or fragmentation. Blue color real but possibly due to gas emission. Non-gravitational acceleration, real but magnitude uncertain. Debris cloud size ambiguous. Measurements conflicting. More data needed. The consensus, natural but highly unusual. Extreme member of interstellar comet population, not representative of average. Not typical, but natural. The artificial hypothesis unsupported by data. No evidence of technology. No unexplained phenomena requiring technological explanation. Speculation continues, but scientific support absent. Mainstream astronomy moves on. Next object. Next observation. Next discovery. 3. iAtlas recedes into dataset, one entry, one object, one point in parameter space. Important, but not unique. Interesting, but not revolutionary. The science accumulated. The knowledge expanded. The field progressed. The universe understood slightly better, marginally, incrementally. The work continues. The final comprehensive observation comes January 18th, 2026. Lowell Discovery Telescope in Arizona. 8-hour integration, pushing detection limit, magnitude 13.8, near background noise. The comet barely visible. Coma measured 180,000 kilometers. Shrinking, tail 40,000 kilometers. Fading, the activity declining. Distance from Sun 2.3 astronomical units. Temperature dropping, sublimation ceasing. Carbon dioxide freezing back onto surface. The comet returning to dormancy, to the frozen state it held for billions of years, to the cold, dark silence of interstellar space. The observation completes. The data archived. The target removed from priority list. 3. iAtlas joins history. A brightness curve. A spectrum, a trajectory, a data set, numbers in database, graphs in papers, footnotes in textbooks. The memory fades, the excitement diminishes. The mystery remains partly unsolved, the questions linger, but the comet gone, invisible, unreachable, the window closed, the chance passed, the moment finished. What we learned, we learned. What we missed, we missed. The universe offered us 4 months. We took what we could. We did what we could. We learned what we could. The rest speculation. The rest remains unknown. The rest travels with 3i Atlas, outbound, forever, into the dark between stars.